So, in this 10th session, we are going to learn about how to perform direct analysis in Stadd Pro. Okay. So, to do that, before we should look at why we should do stability analysis. Okay. So, if you go here, okay. So actually, why we need stability analysis? Okay. Why we need stability analysis? Because direct okay because direct analysis method is one kind of direct stability analysis. Okay, so why we need stability analysis? Because you can see here, still members can fail without reaching yield. Okay, real structures are imperfect. Okay, and buckling is sudden and catastrophic. Okay, modern steel frames are slender. Okay, load combinations amplify instability, and stability design protects against entire frame failure. Okay, frame failure. And old methods like K factor alignment charts are unreliable. Okay, so to counter this, okay, we need stability analysis. Okay, so what are the method? Actually, there is two specified method. One is direct analysis, and another one is uh, effective length method, which is ELM, short term, and this is DM. Okay, but in this model, we will use this one, direct analysis method, because this is superior to this method. Okay, now what are the requirements? If we see what are the requirements for stability analysis? Okay, first of all, we have to consider all the deformations. Deformations include axial load. It may include shear or flexure or any deformation. Okay, so second order analysis, this include port P delta and P small delta. Okay, geometric imperfection, we have previously discussed about notional load. Okay, notional load applied, okay, only for initial imperfection or geometric imperfection. Okay, stiffness reduction, you can see stiffness reduction and uncertainty in strength and stiffness. Okay, so these are the 5 requirements, okay, that the analysis should have. Okay, so you can see here, we have already applied notional load to counter geometric imperfection. Okay, so actually direct analysis method, writing in short, okay, direct analysis method actually incorporate all these 5 requirements. Okay, all these 5 requirements. Okay, direct analysis method incorporate P delta analysis. Okay, it also includes axial, shear, and flexural deformation. Okay, and direct analysis method is done based on reduced stiffness. Reduced stiffness. Reduced stiffness. Okay, whereas equivalent length method is based on full stiffness. Okay, so this is a difference between direct analysis method and equivalent length method. So direct analysis method considered stiffness, reduced stiffness, whereas equivalent length method consider full stiffness. Okay, another difference which is very critical, in case of direct analysis method, if I go at the top, where is KL equal to L? That means KL equal to 1 into L equal to L. That means for direct analysis method, K equal to 1. Okay, so K equal to 1 for direct analysis method. But for equivalent length method, okay, K you have to calculate. Okay, you have to calculate through rigorous buckling analysis, okay, which takes time and sometimes maybe bring some faulty result. Okay, so these are the two basic difference between direct analysis method and equivalent and effective length method. Okay, so we are going to start our direct analysis method. Okay, you can see here in this case K equal to 1, so we don't have to calculate for K. Here you can see in case of direct analysis method, okay, we need a stiffness reduction. You can see here, okay, you can see here reduction. Okay, how it is incorporated? Okay, let's just go to another slide. Okay, you can see here. Okay, so this is flexural stiffness. This is flexural stiffness. Okay, you can see that has been reduced. Okay, this is axial stiffness. This is also has been reduced. Okay, there is another term, this is called tau b. Okay, so this is what is it? We'll learn after some time. Okay, so then you can see the stiffness for both flexural and axial has been reduced. Okay, has been reduced for direct analysis method. Okay, now we will go to our FEM model. You can here see the FEM model. Okay, you can go to load tab and you can go to definition. Here you can see direct analysis definition. Just click here and add. Okay, here you can see you have a flex parameter. Okay, what is flex parameter? Okay, let's go to this slide. Sorry, this one. Here, this tau b is flex. This is flex. Considering considering Stadd Pro for Stadd Pro. Okay, so this tau b actually two types. One is fixed and another one is variable. Okay, fixed and variable. For fixed you can put 1 and for variable you have to calculate. Okay, here you can see for tau b equal to 1 for some specific value. Okay, and for tau b you can find from here for this value. Okay, so these are the parameters. Okay, so if I go for this fixed one, here you can see fixed one. So tau b, that means tau b will equal to be 1. Okay, this is fixed. Okay, if I put tau b equal to 1, here you can see our, if you go there, tau b1 can be used for all members provided that additional notional load 0.00 yi will be added to 0.002 i. That means it will be 0.003 i. Look at this value. Okay, we know our notional load was yi. Okay, if we consider tau b equal to 1 or fixed value, then our notional load will be, okay, clear? So we will use this one, so that will take less time, or will ease or will be easy to complete our model. Okay, so we will use this tau b equal to 1. This is a fixed value. Okay, you can put a variable value, but you have to calculate from here. Okay, you have to calculate from this equation, and you have to put, and it can be changeable. Okay, so but we are not going to that. We will put a fixed value for 1, and we will change our notional load to 0.003 y1. Okay, so now go to model. So tau b equal to 1, you can see. So we'll put 1 as flex means tau b. So add this one. Okay, then we have fy yield distance. So this was value, you can recall. Okay, okay, and this is axial parameter. If I go to the axial if I go to the stiffness, here you can see reduced axial stiffness. Here you can see 0.8 EA. Okay. Okay. So EA. So you don't have to put any data here. It is, so just add this one. Okay. Notional load factor, no, we will not apply here because we have already applied in our combination. So here you can see all parameters you have created, but you have not assigned. So first of all, select flex, and then select all the members, all the steel members actually. Okay, then assign to selected beams. Okay, this one. Only assign to steel members. Okay, select. Okay, so all your direct analysis method has been, direct analysis, parameters has been assigned. Okay, so two more things you have to do. Okay, what are the then you have to go to our, you can see notional load. Okay, if you go here, you can see the value is 0.003, but as the tau b equal to 1, so this value will be 0. Okay, change, you can change from here. Okay. So as the tau b is fixed 1, so you have to put the factor, change the factor to 0.003. Okay, we have changed here. Let's change the factor. Okay. So the value has been changed to all the notional load. Okay. So this is one of them. So another one you have to do, as you can see here, direct analysis method consider, second order analysis, you can see. Okay. Second order analysis include P delta plus P small delta. Okay. So for this, you have to, you have to make load combination linear, sorry, non-linear. You have to make load combination from linear to non-linear. Okay. So after, direct analysis definition and assignment, what you have to do, first of all, you have to change your notional load factor, which is 0.003 from 0.002. Now, your load factor has to be converted from linear to non-linear to account for the second order analysis, which is, P delta plus P small delta. Okay. So you can see here, yeah, we want to save it now. Okay. Save this one. Okay. So here you can see, we have a, load combination. These are all, linear load combination. Okay. So you have to make all this load combination to non-linear. Okay. So to do that, you have to go to, edit input command. Okay. So what you have to do, this is your, linear load combination. So you have to convert it to non-linear. So to do that, you have to, okay, type like this one to make this one. Okay. Load type none. Okay. Type none. Title. Okay. So this like this way, and then you have to enter and repeat. Okay. You can see now your, linear load combination has converted to non-linear. Okay. So I just save this. Okay. Okay. So if we go to our load combinations, you can see here, the load has the, repeated load, which is actually, non-linear load, which has been created. So this two has been created. Now we have to create all these again. I just show you how we have done this. Okay. Go to here. Okay. So go to our edit input file. Go there. You can see how to convert, linear load combination to non-linear. Okay. So you can see here, so if we go to our edit input command file, go to, we have created actually two of them. Okay. So what you have to do, you can see here, these two are, are converted to non-linear load combination. Okay. So what you have to do, just nothing, just you have to delete this combo. Okay. And just copy this. Okay. This one, load type none and title combo, copy here. Okay. Copy here and just you can see you just paste it here and give a enter space and then just copy and then enter here Control D, paste it. If we save it, you can see, okay, third one has been converted to non-linear load combination. Okay, so this is how you can convert to all the load combinations from linear to non-linear. Okay, so what we have to do, just delete this one, copy this whole portion, and okay, and then paste it, just enter. Okay, another one is repeat load, and this repeat load. Okay, Control D. Okay, so again this one has been converted to non-linear. Similarly, okay, I will do, or we will do, all the combinations. Okay, all the combinations here. Okay, so so you can see we have converted all our linear load combinations to non-linear load combinations. Okay, so this is simple. Okay, so what we have to do, just you have to delete combo, and insert a line like load type, like load type none, title combo, and you have to paste repeat load. Okay, so this is the format you can see here. This is the format we have applied to all the load combination to convert it to non-linear load combination. Okay, so this is how you can see our load combination have been converted. Okay, so let's take a summary. So what we have to do, so first of all, we have to go to our definition. Okay, sorry, this is the definition. So flex is one, flex wants mean this is actually tau b. Okay, then FYLD, yield strength, and then HCl. Okay, so we have to put this value and assign this value to all our steel members. Okay, another thing we have to do, okay, so we have to go to our load cases, and for notional load cases, okay, you can see here, we have to convert it from you can see, you can see here, we have to convert it to 0.0003 0.002. Okay, as we have considered tau b equal to 1, a fixed value. Okay, and then we have to convert all our load combination from linear to non-linear. Okay, so this is how direct analysis can be defined in Stadd Pro model. Okay, now what we have to do, we have to go, one thing is remaining there, we have to go analysis. Okay, you can see we are doing direct analysis. So direct analysis, so number of iteration, you can put 15 to 30. Okay, I'll just put 30. Okay, LRFD. Okay, so just add. Okay, so you can see perform direct analysis. Okay, iteration. So another thing you have to do, go to your edit file. Okay, once again, you can see there is a line, perfect perform direct analysis LRF iteration. Just enter and type load list. Okay, load list. So our design will be from these combinations to these combinations, like our combinations are from 101. You can see here. So this is our first combination. Okay, so what is the number? You can see here, this is the number 101. Okay, so from 101. Okay, so this is our last combination. What is this? 168. So load list 101 to 168. So software will design following only these load combinations. You may have more combinations, but you can define software for which combinations software will design for your members. Okay, so from 101 to 168, you can see our last combination, this one. we can have more combinations, no problem, but we will not include in our design. Okay, so keep this in mind. Okay, load list, you have to finalize your load list. Okay, here you can see uh, you know, so this is how you can, perform direct analysis. Just click a save. Okay, and then close it. Okay, now you can see we have performed our direct analysis or stability analysis. Okay, so this is the way you can perform direct analysis or stability analysis. Okay, so stay tuned for next class. So in this next class, our analysis has been complete for this model. Now we will see how to design. Okay, how to design any particular structural member or whole FEM model. Okay, so in the next class we will discuss about how to design. Okay, in Stadd Pro. Okay, so for the time being, stay tuned. Okay, and thank you for watching.